Okay, so second speaker is Ofer Zeitouni. We'll speak about minima frontal trigonometric polynomials. Thank you.
Thank you. It's good to see everybody, even if only through a screen, and only those who are not blacked out. My talk is going to be a very specific one. I hope to give you more or less the essence of the proof. So it's a joint work with Ofer and Yakir. Along the talk, we will see pictures of various people. They are all taken from the internet. And it creates some interesting things to chase for these pictures, but anybody interested can ask me in private. Okay, so what am I going to talk about? I'm going to look at random polynomials and specifically the simplest form of random polynomials, which is not necessarily the most natural one, but it's definitely the simplest to describe, which is just a polynomial of degree n with coefficients zeta j, where these zeta j's are just IID random variables, which we are going to insist have zero mean. For most of the talks, they will be Gaussian, but not for all. So at the moment, those are just IID random variables. So, so such a polynomial has zeros in the complex plane. There are n zeros denoted zi, and you can ask all sorts of questions about them. So in particular, you can ask about the empirical measure. And if you simulate it, if you go to the internet and look for a picture, you'll find a picture of simulations of such empirical measures. If you look very carefully in this picture, you will see that here the coefficients are real because the zeros are coming in complex conjugate pairs. So, this fact is well known, that zeros cluster around the unit circle, and in fact they cluster uniformly around the unit circle. This is very old; those are very old results of Erdos and Turan, Sparrow and Schur. There's a very nice, modern, and quick proof of this fact, which is based on a deterministic fact, looking at the logarithmic potential associated with the empirical measure. So the result is that the distance in any, essentially, was there a question? The distance, just a second. So the distance, the bounded Lipschitz distance between the empirical measure and the uniform measure on S1 is bounded by this gizmo, which if you look at, so this is a log of the sum of the absolute values of the coefficients, minus 1/2 log of the first plus log of the last coefficient. In typical situation, Mn is of order log n. And so you see that the empirical measure converges nicely to the uniform on the C. Okay, so.
Please excuse me one moment.
Sorry?
Excuse me one moment. The coefficients, are these zeta or eta?
Zeta. Oh, I'm sorry. This is a typo. So
okay.
Those should be, thank you for pointing this out. So those are zetas. Thank you. Yes. Okay. So this is a random polynomial we are looking at, and since these results have appeared, a lot of work has been done. So let me just very quickly relate to that. So there has been a thread that dealt with the expected number of real roots. So this goes back to famous questions of cuts and to work of Ibragimov and Maslova, Shep, and others. so those of you who work on such question know about the Katz-Rice formula. So the origin of the Katz-Rice formula, at least on the cut size, is exactly in dealing with such questions. There are results that came later, although mathematically they could have come early, which have to do with the density of the expected number of zeros near the unit circle. So we know that the zeros converge to the unit circle, but you can blow up. And the blow up, the natural scale is of order 1/n. And when you blow up like that, you can ask about what is the density of the expected number of zeros near the unit circle. You can ask questions about the point process after you did this blow up. In particular, what are correlation functions? What can you say about the spacing between zeros? Very much mimicking questions that have been asked in the context of random matrices. So there has been a thread of work on that in the last decade. You can ask questions about variance and concentration, etc. Okay, so this is kind of a rapid history that brings you up to speed about what has been done about zeros of Katz polynomials. Now we are going to be interested in a slight variation, namely we are going to look at this polynomial as a trigonometric polynomial, namely when the argument is on the unit circle. So now it is not at all clear that there are zeros. If you look at the real part of Pn, then you have a one-dimensional parameter and a one-dimensional function. So there is no reason, no structural reason there should be no zeros. And in fact, there are zeros. And there has been a thread looking at that. So in the Gaussian case, the expected number of zeros is known, is explicit. And the variance has been computed about 10 years ago by Granville and Wigman. In the non-Gaussian case with bounded moments, the expectation is of the same order, even though there's an error term, and the variance has been first shown to be of little order of the mean square by Hoy and Wu, and then they computed up to a constant by Bali, Caramelino, and Coli. So, but you can see from the years that we are getting closer to the present time. And there is also a side result that I'd like to advertise that for this exact question, you actually can get large deviation type bounds or concentration type bounds concerning the number of zeros around the mean. Okay, so that's about the real part. But now, and I should also add that all these questions have been raised in the physics literature by Bogomolny, Bohigas, and Leboeuf in the context of creating different models of point processes of interest. And also this thread connects to advances and results on Gaussian stationary processes. So this, there are mostly in the two-dimensional case, there are results of Nazarov and Sodin, and then there are more recent results of Feldheim and Nitzan, and others, which I'm not going to review first. Okay, but what I'm going to talk about is slightly different, and it also has some history. So it goes back to work of Konyagin and Schlag. And what we are going to do, we are not going to look at the real part of Pn, but actually on Pn. And for most of the talk from now on, we are going to talk about coefficients which are centered complex Gaussian and IID. I will say something about this assumption later on. And it's easy to see from basically from Fubini that almost surely there are no zeros on the unit circle when you look at this complex polynomial. And so that's not a natural question to ask about zeros if they don't exist. Instead, we're going to ask about the polynomial itself, namely look at the minimum of the polynomial. This, of course, is influenced strongly by the presence of zeros in the neighborhood of the unit circle. And the question, which goes back to Littlewood, in the case of Rademacher random variables, is what is the order of Mn? Now, you will note that I normalized my polynomial such that its variance is 1. So this 1 over square root 2n plus 1 is just a normalization. It makes, in the case of centered Gaussian complex coefficients, it makes the polynomial invariant under rotation n of variance 1. Okay, so that's the question, and now comes the first results about that. So in a couple of papers, first by Konyagin, who proved the first statement you see on the slide, and then by Konyagin and Schlag, who gave a complementary lower bound. What they showed is that for Rademacher coefficients, the right scale is 1 over n, at least to leading order in the exponent. So what they showed is that the probability that Mn is much larger than 1 over n goes to 0. And for both Rademacher and Gaussian coefficients, it cannot be too small. So the probability that it is smaller than epsilon over n is bounded by a constant times epsilon. Okay? So this gives us a ballpark. We know where we are living. We are living somewhere at order 1 over n. And a natural question is, can one say something better? So I repeat the polynomial. And here is a theorem that I want to advertise. So the theorem tells you that not only the scale is really 1 over n, but in fact, there's an exponential law with an explicit parameter. Okay? If there are, I cannot see while I'm showing the controls if there are questions, but if there are, maybe someone can, the organizers can interject and let me know. Okay, so that's a theorem, and as I said, I hope to give a more or less full sketch of the proof. Okay, now that's a very nice theorem. So this is Seger Rishon. This is a Corona theorem, and luckily there was a Seger Sheni because. So there was a second lockdown because during this time, Cook and Nguyen have managed to prove a complete universality result. Namely, they show that the limit distribution of NMN is universal under very mild assumptions on the coefficients. In particular, the result applies to Rademacher variables. Okay, so that's kind of the state of the art. It closes the question, but I'm not going to talk, except for a few remarks at the end. I'm not going to talk about the results. Okay. So first of all, let's when you see that, you tell yourself, okay, it's a Gaussian process, so let's try to do some back of envelope computations. So first of all, we have a correlation. We can compute the correlation of this Gaussian process, and you can see that the process decorrelates at scale 1 over n. Okay. So you would tell yourself, okay, this is a process that decorrelates at scale 1 over n. So essentially, it should behave like n independent variables. Okay, so let's continue with this kind of heuristic. What is the probability that at a particular point, you are at scale constant over n? Well, you have, at a particular point, you have two independent standard random variables. You want both of them to be smaller than 1 over n, because you want the L2 norm, say, to be smaller than 1 over n. So the probability of that is 1 over n squared. So this gives you pause, right? If we know this is a correct scale, but we have 1 over n squared for the probability at a particular point, and on the other hand, it's enough to look at n points, something is wrong, right? Because n times 1 over n squared goes to 0. So that would seem to suggest we are not in the right scale. And of course, this is not quite the right thing. The basic observation is that it is true that it's a polynomial, but you could ask to what scale can it be approximated by a linear function? Right? It's a nice analytic function, nice smooth function, so you can tailor expand it. And it turns out that it goes to the linear approximation is valid at a scale which is relatively large. So it could be that, so let me draw a picture. It could be that at a particular point, say if this is 0, the value is large, but you have a linear line that gets closer to 0. Closer to, so I'm drawing here, this is at a particular point, and I'm drawing it as a function of the distance from 0. So maybe I'm high at 0, but somewhere along this linear line, it's very correlated because it's just linear and I know the coefficients, I will get much closer to 0. So that's the story of what is going on. There is a natural scale for linear approximation, which is much larger than 1 over n squared. And this motivates taking some skeleton, even though the variables are very correlated, to take some skeleton of order of 1 over n squared, and then look at equidistributed points on the circle. And now what we would like to say is, okay, we can, for all these points, replace the complicated polynomial by a straight line. And that will depend on only two parameters, the value of the polynomial at the center at x alpha, and the derivative at that point, okay? So we have these points, we have these parameters, and now we ask ourselves, okay, I have a linear function, this linear function, which is a good approximation of my polynomial. And what am I interested in? What I'm really interested in is to look along this line, to look at it as a function of x minus x alpha, and to look at the point where the distance is minimal. So, okay, that's something you can give to your favorite high school student. And you can solve it and make sure you're not making computational mistakes or typos or things like that. And you get an expression that the distance is the absolute value of this quantity, which I circled here. Okay, so you should trust me. One can do this exercise. So that gives us a candidate to associate to each point some kind of minimal value. And of course, because the polynomial and its derivative are relatively correlated on adjacent points, the value will not change too much between adjacent points. Okay, is that clear? So if you believe that my polynomial is well approximated by a linear line to a distance much larger than the spacing between the points I took, then certainly you can, it's clear that the value of the minimum you will find will be more or less the same for adjacent points. So, okay, so how are we going to count, or how are we going to look at these small values? So we introduce Y alpha, which is a proxy of the location of the minimum, and Z alpha, which is a rescaled version of the value of the minimum. And the high school exercise told you that Z alpha is essentially the minimum of this linear approximation. So now we are going to ask for two things from a point. We're going to ask if we want to count points where the minimum is small, but we don't want to overcount. We don't want to count it both for a point and its neighbor. So we are going to put two conditions. The first condition is that the value is wherever we want it to be, which means, say, smaller than n to the -1/2. And disregards these conditions. Those are just technical conditions. Forget about them for a second. But the important thing is we are going also to ask for the minimum to be at the interval I alpha. So if I have a linear approximation that extends over several, I'm drawing it a one-dimensional picture, although it's a two-dimensional picture, really. If it extends over several points, then I'm only going to count this guy, because this is where the minimal distance occurs. Okay, later maybe the distance is larger. So that's what these conditions are. The location is where it should, where I'm counting, and the value is what I want it to be. Okay? Good. So it's an easy computation to check that you are going to catch the minimum this way. Namely, the possibility that there exists a minimum that will not be counted by these events on our lattice, on our collection of sample points, is going to be negligible. So this is just not going to happen. So as far as we are concerned, we have replaced the original problem by a counting problem. We want to find how many of these A alpha occur. If none occur, it means that the minimum is larger than n to the -1. Okay. So this is really what I'm writing here. So we want to count these good points, and we have. Now, there's of course a typo here. I'm sorry. So it's not Pn smaller than A. It should be smaller than A over n. Okay, so there is a well-honored method for getting Poisson limits, which is based on Stein's method, and it's called two moments suffice. So I'm sure many of you know it, but for those who don't, let me review what it means. So now forget for a moment about the random polynomial, and let's ask the following question. I have random indicators Q alpha. This should be expectation of Q alpha. Okay, so I have a collection of random indicator Q alpha with P alpha as the expectation. And the sum of P alpha is lambda. Okay? So you should think of alpha taking values in a large set, but P alpha being small, such that the sum is of order lambda. So this, if the Q alpha are independent, this is exactly the regime in which you will have a binomial convergence to Poisson. And what we may ask about are conditions for the random sum to be Poisson distributed. Okay. So as I said, if the Q alphas are independent, then it's an easy computation. You just compute the probability and you use a multinomial distribution. But if they are not independent, it is not so easy. So a standard method to approach this question is to introduce what is called a neighborhood of dependence. So for example, imagine that each Q alpha depends only on its neighbor in some kind of weak dependence. Then obviously you could just count, you could split the sum into sums over pairs. And if the two, so let me write it here. So if, for example, Q alpha is only dependent with Q alpha plus 1, but independent of rest, then I could just simply write sum of Q2 alpha plus Q2 alpha plus 1. Those would be independent, and all I would need to say is that the probability, if I also knew that the probability is that both Q2 alpha and Q2 alpha plus 1 occur, this probability is little order of P alpha, then I could apply the result about sum of independent variables. So what I'm going to describe next is a method that kind of abstracts this observation. And it introduces a neighborhood B alpha. So these are collection of indices which you think somehow the Q alpha depends only on these guys. And then you can introduce several quantities. So the first quantity, denoted B1, is just the product of the deterministic number P alpha, where alpha is going over everything. So sum of P alpha, we agreed, is essentially lambda. This sum of P alpha is lambda. And then all this means is that B alpha is not, if you want B1 small, it means that B alpha is little order of the total number of points. B2 is a more complicated quantity. It captures the fact that the correlation, while existent, is weak within B alpha. Namely, that the probability to have two successes in the neighborhood, so that are close enough, this probability is small. So this is B1 and B2. So that takes care of local correlations, like in the example I mentioned earlier. But is that enough to get the Poisson limit? So the answer is no, because there could be some long-range correlation. So we would need some control on long-range correlation. And this control is going to be given in the following way. So you look at Q alpha minus P alpha, and you condition on how many successes you had outside of B alpha. Okay, so the situation is I have an alpha here, I have a neighborhood around it, which is my B alpha, and I condition in our, say, if I apply to our setup, I condition on how many successes I had in this great arc. Okay, and if that quantity is small, it somehow means, because if I did not condition on the sum of Q beta, if I did not condition on that, this expectation is just 0, because the expectation of Q alpha is P alpha. So somehow this condition tells you that what happens outside the arc is not so important. And so these are the quantities. I've introduced it, so I remind you of the notation. And there's a theorem, a famous theorem of Aratia, Goldstein, and Gordon that said that the variation distance between the law of sum of Q alpha and the Poisson law is bounded by the sum of these coefficients. Okay? So if you know that B1, B2, and B3 go to 0, you know that you converge to Poisson. Okay? So this looks great. It's one of the most successful applications of Stein's method. There have been many generalizations of this fact to compound Poisson, to other type of convergence, etc. But this basic result, which is actually not very, the proof is not very long, is very often useful. Now, you note that B1 and B2 involves only first and second moments. So those are relatively simple to compute. But in spite of, so the title of the paper is that 2 moments suffice for Poisson convergence. And in spite of this title, you should look at B3 and that should give you pause, because yes, it's a moment, but it's a conditional moment. And can we do it? So we need to condition. If we are looking at that, we essentially get information. If you think back in our setup, we get information on the polynomial at many points. And not only many points, but the size of the complement of B alpha is going to be much larger than n. It's going to be almost n squared. Anyway, you're going to do it if you want to make B1 and B2 small. So this means that I'm conditioning, if I replace this conditioning on the sum by conditioning on the actual variables, then I'm completely dead because everything is deterministic. I have a polynomial of degree n. I sample it at n square points, I can reconstruct it everywhere. So I can know deterministically whether Q alpha occurred or not. In particular, there's no hope that this quantity will be small. And if you think further about that, it's not clear how to take into account this complicated conditioning in order to estimate the conditional expectation of Q alpha. So our conclusion was that this is too hard, and in particular that we need to do something different. Okay, so that's what I'm going to describe next. So we want now to look at it differently. So remember that Z alpha was a proxy for the value, and A alpha was a condition that said that the minimum occurred around the small x alpha. So what I can do is I can look at, so if I'm at A alpha, I would like to keep the Z alpha. If I'm not at A alpha, which means that the minimum is occurring, the local minimum is occurring somewhere else, well, that's, for me, that's as if it's infinite. So now I'm going to introduce a new process, which is a point process. So I'm summing a Dirac mass at each of the values of the local minima. Okay? So this is Mn, and this is a point process. And what can we hope? Well, since minima are created by good x alpha, this we saw already before, namely the linear approximation locally is a good approximation, then having no minima in the interval, no minima in absolute value smaller than A, which means that Mn of the interval minus A is 0, this is the same event up to something negligible as the event Nmn is larger than A. Okay? Where Mn, I remind you, that Mn was just the minimum of n Pn of z, where z is in S1. Okay? So all the information we care about is contained in this point process Mn. And now the question is whether we can analyze this point process. So first of all, if you want to analyze the first moment, you can try to compute the expectation. Well, the expectation is simple because if you look at the event, the event that x alpha is in minus AA, this is a simple question involving a pair of Gaussian random variable, P and P prime at the point x alpha. So you can compute it. And when you compute it, you get something that makes you happy. You get a constant that is proportional to A. Okay? So the expectation is proportional to A. That's very nice. So the main theorem will therefore follow if we show that the probability that we are 0 is just e to the minus 2 lambda A, which means that we are trying to show that Mn as a point process on R is just a Poisson point process. Okay? Now, I would like to emphasize one thing. There is a transformation that I have glossed over, but that will turn out to be crucially important. Originally, I cared about minimum, which are positive random variables. And I've transformed the question to a question on R. So, of course, if you take absolute value of a variable in R, you will get something in R plus. But this transformation is going to play a very important role, as we will see momentarily. Okay, so this is our goal now. So we have this point process that I have defined. And the theorem, now you should not be shocked by this theorem, is that the process Mn converges to a Poisson point process with parameter lambda. Okay. And in the rest of the talk, I want to explain how do you prove that. So the proof is actually relatively soft. It is based on a theorem of Liggett, and it is based on a theorem of Liggett using a method that was devised by Marek Biskup and Ofer in their study of the Gaussian free field. So let me tell you what is the theorem of Liggett I'm referring to. So suppose that I have a point process on R. So when I write it like that, I really should have written, maybe it would have been written. So this means that P is sum delta xi. So I'm not looking at the process xi as function of I, I'm just looking at the point process. And suppose that I told you the following information. For some collection of IID random variable yi that are independent of P, P has the same distribution as xi plus yi. So if I have my original point process, I'm thinking of it as a point process on R. My transformation is just going to create a new point process, which is going to look like this. This will be my new variable. Maybe this one will come here. Maybe this one will come here. Maybe this one will come here. This one here, etc. Okay? So this is a transformation xi plus yi. It gives me a new point process. And the assumption of Liggett's theorem is that this point process, the red point process and the black point process have the same law. And suppose further that the expected number of particle in an interval of size b minus a is just a constant. Then P is a Poisson point process with parameter lambda. So this is This is a characterization of Poisson. Of course, Liggett's theorem is infinitely more general. It applies, it gives limits which are not Poisson processes, but rather mixture of Poisson processes, and not necessarily with constant intensity, but rather with exponentially decaying intensity. But the constant intensity case is the constant intensity. In the constant intensity case, there's a further simplification that the limit you get is a clean Poisson, is not a compound, it's not a mixture of Poisson. Okay, so that's the theorem. And now the question is how to apply the theorem to Mn, and where do I have my xi and what are yi, and how is it all related? So my xi, I know what they are. Right, I have defined this variable z alpha, and my point process was sum of delta of z alpha. So that's kind of obvious what it is. So in order to tell you how to apply Liggett's theorem, there are several steps that I need to tell you. So these are not hard, but those involve a little bit of computations. So the first step, I'm going to claim that Mn is a tight sequence of processes. So in particular, if you look at the topology of the convergence of point processes as convergence on compacts, then it's enough to check that Mn on the interval minus AA is a tight sequence. And that's a first moment computation. We already computed the mean of that. So the mean is bounded, so independent of the L, so certainly this is a tight sequence. So possibly taking a subsequence, we know that Mn has a limit. So let's take that limit, let's call it M. And now we want to identify M. If I'll show you that M is a Poisson point process, then there is nothing else to do. Okay. So that's the first step. The second step is the following. So the second step says that if x alpha and x alpha prime, the prime here is misplaced, it's like that. If x alpha and x alpha prime are close, okay, you cannot have a minimum in both of them. So this comes essentially from the approximation by the linear functions. And this is related to the conditions that I called B2 in the two moments suffices. So in words, what this condition tell you is that points that are mesoscopically or microscopically separated cannot both contribute near minima. Okay? So I will not have a situation where somehow locally I create a lot of minima. This is why in my definition of the point Z alpha, I insisted that the location of the minimum is in the interval IR.
Ofer?
Yeah.
Is that union over the distance greater than n minus epsilon or less?
Less. So it's a union over pairs, and you want both of them to succeed. So it means that points that are not macroscopically separated will not create a minimum. Right? So let me draw a picture. Maybe this will clarify. So I hope I'm not making a mistake here. Of course, if you ask me a question, I'm immediately nervous that I'm making a mistake. But so x alpha, you have a value here. Okay, what this event would mean? It would mean that this guy is down here, and also this guy is down here, right? That's what this means, where the distance here is small, is n to the minus epsilon.
Mm-hmm.
Okay, but if you believe the linear approximation, this cannot happen because the curve is like this. And it's not in this scale, so my curve drawing is misleading. So the curve is going to be something like this. So if here I'm low, I cannot be also low here. Okay?
Okay.
And this is the event that is written here. So points that are close together cannot create distinct minima. Because remember that the event A alpha means that the minimum really occurred at this location. It's not just the value, it's the value and the fact that the minimum occurred in this location. Okay, so this is, as I said, this is exactly the same as control on B2, on these local correlations. It just says that essentially it rules out the possibility of getting a compound Poisson. Right, and getting an event in which suddenly you have 2 points and not 1. Okay, so this makes near minima macroscopically separated, and as you can see, it involves only a second moment. And so the high school exercise plus the computation of the second moment make sure of that. Okay, so this is half a page of computation, not very hard. Good. And now comes the Biskup-Louidor trick, and now comes the place where we are going to use the fact that my coefficients are Gaussian. How? I'm simply going to write my zeta j as square root of 1 minus epsilon square zeta j plus epsilon eta j. Well, now the zeta and the epsilon, this equality is in distribution. Right? I can decompose a Gaussian variable into a sum of 2 Gaussian variables with the proper variances. Okay? So I got my Pn as a sum of a Qn and an Rn, where Rn is independent of Qn. Okay? Good. So, so we have that. And we are going to take the epsilon to be 1 over n. And in that case, you can check that n times, not qn, but n times rn is of order 1. Okay, that's just a variance computation. And now you show the following. So first of all, remember that we care about small value of Pn, which means small value of Qn plus Rn. So the first thing you show is that in order for Qn plus Rn to have a small value, Qn has to have maybe a slightly larger, but of the same order small value. So Qn cannot have a value which is very large, and Qn plus Rn has a small value. This is just not going to be how the minimum occurs. So that's again essentially a first moment computation. The second point that you should realize is that the small values of Qn, or I should maybe say the small value of Qn, which are candidates for being minimum, those are created by the events A alpha, and they are separated. As we saw before, Q cannot have 2 close near minima. That was the point about the B2 condition. Okay? Which means from these 2 facts, what can you conclude? Well, you can conclude, first of all, that you need to look at near minima of Q. And second, that these near minima are macroscopic or almost macroscopically separated. And also there are not too many of them by the tightness. So the tightness makes sure that there is order 1 of such points that you need to worry about. But now you are looking at order 1 points that are essentially macroscopically separated. And what do? You add to them something related to Rn, right? But what is Rn? Rn is like our original polynomial, okay, which is going to be of order 1 over n, which is exactly the order that we care about. So this additive perturbation is just going to kick your value by some constant, by some random variable. And these random variables are going to be independent at different points because of the macroscopic separation. So in short, what you have is that at each small value of Qn, the effect of adding Rn is to add an independent random variable. And this kicks, this shift in the value are independent because of the scale separation. Okay? And that's it. Now you can apply Liggett's theorem. You've got yourself the xi, which are the near minimum. So the x alpha are the near minimum of the Qn. And then you add to it the y alpha, which are the value of Rn, of this guy, which is of order 1 over n. And they're independent of it. They're completely independent. And they're independent between themselves. So of course, you have to make it slightly quantitative, but that turns out not to be a problem. So this gives Liggett's theorem. As I said, this beautiful trick is due to Biskup-Louidor in an infinitely more complicated context, but here it really works very nicely. Okay, so that's the proof. Let me give you some concluding remarks, and then I'll finish and answer questions and so on. So first of all, moving to a process on R instead of R plus was crucial because I don't know a version of Liggett's theorem on R plus. It looks a little bit silly, but I don't know any of those. So in particular, I don't know, of course, if you are on R plus, you cannot simply add an independent variable that is both positive and negative, or you cannot add an independent variable that is always positive because that would not have the same law. And if you add a random variable that is possibly negative, you get out of R plus. So that invariant cannot work on R plus. And the idea to move to R, which is really this high school exercise, which said that, I can, instead of looking at the distance, I can look at the sign distance. This was crucial. So without that, I don't know. I don't have it. The second comment is that essentially the same result and the same proof works with Pn with real Gaussian coefficients. That you could believe me. That's not very hard. The third remark is slightly more subtle. So you can apply the invariance if the entries are not Gaussian, but the law has a Gaussian component. So what do I mean by that? So suppose that my zeta j to start with was equal to alpha gj plus beta, eta j, where gj is Gaussian and eta is not. Then I could apply it by just doing the Liggett trick on the gj component. Now, what turns out, so for those of you who followed what has happened in random matrices in, let's say, in the last decade, this was the first step in order to get universality. There was a beautiful result of Johansson that shows that all the spacing distributions that were proved for GUE by explicit computations work if you have this kind of entries by some extra computation. I don't want to get into that, but the point was that you could get the same result once you had entries that had a Gaussian component. So that's more or less obvious that this would work here. But what is slightly more surprising is that you can even have here an alpha n and a beta n where alpha n goes to 0, and it still will work if alpha n does not go to 0 too fast. So this gives you a large class of coefficients. Unfortunately, the rate in which it goes to 0 is too slow to allow you to use Rademacher coefficient or a smoothing of Rademacher coefficients. And in fact, I don't know how to push this all the way to get Rademacher coefficient. So we thought about it for some time, and we don't know how to do it. even though it's a very tempting direction. What Cook and Wayne do is we essentially looked at this point process. And what they do, they prove universality by just saying, okay, forget about how you proved that AN is going to be Poisson. All I need to do if I have other Z alphas that come from non-Gaussian coefficients is to convince you that the moments of AN are the same. So if I show you that all fixed moments of AN coincide, I'll be happy. Now, Z alpha is a sum of independent, not identically distributed, but independent random variable. So the moments of AN of alpha involve basically a counting of points for a multidimensional vector. So what you need really, if you are going to do it this way, is to compute a local CLT with a high precision. And that's what they do. So they do a very delicate, which involves a lot of combinatorics, multidimensional CLT. It's a combination of tools that have been developed by Wayne and others in the last few years. There's a healthy dose of Fourier analysis that comes into it, but not only. There's a non-trivial combinatorics showing up. And they manage to prove a multidimensional CLT. They don't identify the moments because it's too difficult, but all they do is that they show that the error terms between the Gaussian and non-Gaussian coefficients are small. And therefore, the leading order, which is a moment of AN of alpha, which we know is non-trivial by the tightness, is the same for Gaussian and non-Gaussian coefficients. Okay, so that's the story. Thank you for your attention.
Any questions for Ofer? And if someone has questions for Clément, I think it's also possible. He's still here. Yeah, so I had one question for Clément. It's also for Ofer, because joint paper. So you had the theorem that assumed some heat kernel bound. So if you assume it's a Gaussian heat kernel bound, then wouldn't you get something like an invariance principle, which would immediately tell you something?
I did not understand the beginning of the question.
So if you assume as a condition that you have a Gaussian heat kernel bound for the work, can't you immediately deduce something about the disorder? Just by some kind of invariance principle or something like this?
Well, if they are Gaussian, I think it doesn't help much more from what I understand. It doesn't help much more than the case where it's not Gaussian. No, the same problem appears with a uniform heat kernel, uniformity or not uniformity. For example, for the percolation cluster, you have these Gaussian heat kernels, but they are not uniform. So I think it's more about that. And yeah, at least I don't know.
But in the weak disorder setup, there are central limit theorem for the tilted measure. So if you're going to be in the weak disorder setup, then by the theorem that Clément mentioned, the theorem of comets and company, you do get some results on CLTs, but you should remember that everything is weighted by the disorder, and it's an exponential weighting. So what weak disorder is doing very roughly is, certainly when beta 2, not just weak disorder, but when beta 2 is positive, essentially the number of intersections is finite, So you can look at it from the point, I mean, there's a way to transform it to some kind of Doglin chain. And the CLT becomes a CLT for a Doglin chain. I know that I'm vague, but that's what happens. And so the exponential weighting does not bother you because you have the beta 2 positive. Then you still can show. So this is a technique I see Noam there. This is a technique that Noam knows quite well. So anyway.
Ofer, I have a question to you. So you started from the zero distribution of Katz polynomials. You said that there is some relationship between the order of the minimum and the zero distribution. Do you deduce something like the distance of the closest zero is 1 over?
No. What I meant is more in some heuristic way. It's not a precise relationship, but of course, if you have zeros close by, then the minimum would go down.
So
your result, you would believe that the location of the minimum, for example, is where you have close by zeros. But I don't know how to make that intuition precise.
But the intuition says that close by means distance 1 over n from that point.
Yes, but there are lots of zeros. Most of the zeros are at distance 1 over n.
Right. So this is
actually it should be much closer than 1.
Yes, that's
closer than 1 over n.
Right. And another thing. People sometimes look also at the infinite power series. Paris and Virag were studying the zero distribution of the infinite power series. It was determinantal. Any relationship here? Could you say that the truncation of the infinite power series is near the unit circle has some resemblance with the infinite power series itself?
So for the question we are looking at, of course, you cannot look at it for the infinite power series. So you have to do something, and one thing you could do is truncate, which is what we are doing.
Right.
So, we are looking at the beginning of this infinite power series. I think that what you know is that the distances which are much larger than 1 over n, certainly at macroscopic distances, the point process converges. So the point process of zeros of the Katz polynomial inside the disk at a bounded distance converges to this determinantal process that appears in the limit. And I don't know if this is completely resolved, but I would expect that at distances which are much larger than 1 over n, this is still correct, true. But this has nothing to do with the distances that affect the minima as I expect them to be. Okay?
Right.
So it's really a question already on the truncation, and I don't know how to ask this question even on the infinite power series.
And still, sorry, about this infinite power series, can you not make any sense of the values in the unit circle? Is it maybe a distribution of some sort, or nothing can be said?
Yes, but you cannot make sense of the minimum.
I understand, but maybe afterwards there is something that is affected.
So, okay, so one thing you could try to do, I don't know if this works or not. In exactly the same way that for log correlated field, you create a measure by taking the exponential of the log correlated field and looking at integrals. You could try to do something like that here. The minimum. Sorry? Yeah. So you would take the log of the log of Pn with a negative sign if you want to see the minimum.
Okay.
And you would put e to the minus beta log of that. And the question, the question we are asking is kind of a phase transition in beta.
Right.
So what happens is that there will be there should be a freezing transition at some beta that corresponds to when the minimum takes over. And that would make sense as a limiting process. So that measure has a good chance for beta smaller than the critical beta that measure has a good, I'm pretty sure that you can prove that.
I see. So there is something, yes.
Yeah. So you can define such a measure, etc. And you have the usual issues, which is at the L2 phase, the beta 2 finite phase is going to work relatively easily because it's just a computation of second moments. But if you want to go to the whole L1 phase, you need to work. So that's...
All right. Thank you very much.
Any further questions? If not, let's thank both our speakers of today. And next week we have Boris Khalid from Princeton. It will be 2 hours talk about neural networks and connections to probability theory, where the first hour is essentially going to be a literature with a very general talk, and the second hour will be about actual results. So, he's a wonderful speaker. And,
can you repeat the name of the speaker? I couldn't hear.
Boris Khalid. Okay, so thank you all, and you can stay to discuss if you want. I'm going for lunch. Enjoy. Bye.